This is the 10th in a series of revision videos to help you practice pure factual recall of the facts that are listed in your A-level chemistry specification. So no analysis or evaluation, just the facts. There's a little bit of overlap with the AS chemistry equilibrium video, but if you haven't watched that already, I would suggest that you go there first. The link to the questions in this video is in the description below, so download that worksheet and work through the questions before using this video to check the answers. Chemical equilibrium happens when a reversible reaction occurs in a closed system, and the two key aspects are that you're going to have unchanging concentrations of the reactants and products, and this happens because the forward and reverse reactions are occurring at the same rate. So the concentrations of reactants and products are unchanging, they are not the same as each other. We're going to use Kp as our equilibrium constant rather than Kc when we're talking about gases, but also when we're talking about gases and we have partial pressures rather than concentrations. So it is actually possible to use Kc for a reaction involving reactants in the gas phase, provided you know how large the volume that they're in is. It's only when we only have partial pressures that we have to use Kp. A homogeneous system is one in which all of the reactants are in the same phase as each other. To look at which way equilibrium will shift if pressure is increased, we need to use Chateliers principle. So this tells us that whatever we do to a system that's at equilibrium, if it's a closed system, their system will shift to counteract the change. And so in this instance, if we're increasing the pressure, the system is going to shift to decrease the pressure, and therefore it's going to shift in whichever direction will remove moles of gas. So therefore it will shift to the side of the chemical equation that has the fewest moles of a gas. In a similar way, if we're looking at the impact of temperature, again, the Chateliers principle tells us that the system shifts to counteract the change, and so if the temperature has been increased, it's going to shift to decrease, and therefore that will favour the endothermic reaction. So whichever reaction is endothermic, whichever reaction has a delta H value that is positive, that is the reaction that we favoured, and therefore the equilibrium will shift accordingly. If we consider a mixture of gases that are contained within a vessel of a particular volume, and we then imagine a hypothetical situation where one of those gases was removed and it was placed into a new vessel that had the same volume as the initial vessel, partial pressure is the pressure that would be exerted by that individual gas on its own in that vessel that has the same volume it was in initially. The mole fraction is the proportion of moles in a mixture that are the particular gas that we're interested in. I've described it as a proportion rather than a fraction because, frustratingly, even though it's called mole fraction and even though we should really express it as a fraction, very, very often in the exams they give it to you as a decimal. So proportion just makes more sense in my head. If we're going to write an expression, we do write this as a fraction, so we have the moles of the gas that we're interested in divided by the moles of all of the gases. To figure out what the partial pressure of a particular gas is, we take that mole fraction that we just worked out and we multiply it by the total pressure. So if I'm going to write a complete expression, we'd have our moles of A again divided by the total moles and then that multiplied by the total pressure for the reaction mixture. If we're going to write an expression for Kp, there's a little bit of variation between different books and different ways of writing it. So essentially what we're going to have is we always have the products on the top and the reactants on the bottom, and we always have things raised to the power of however many moles there are. So we're going to start out with Pc times Pd cubed divided by Pa times Pb squared. Now, depending on which book you're used to using, which system you're meant to use, you might also have encountered having Pp for partial pressure, which is also fine, and you might also have encountered using brackets, and some people put brackets around the reactant, and some people put brackets around the entire thing. And any of these methods of writing it are completely fine. So don't worry if yours looks slightly different to mine, that's okay. Rather like Kc, Kp is only going to change if you change the temperature. And in order to work out whether it's going to increase or decrease, we need to know whether the forward or reverse reaction is the exothermic one, and likewise which is the endothermic one. So firstly, what we need to know is that if Kp increases, that tells us that we have more products, because of course the products are the numerator of that expression. So as the partial pressure of them increases, the value of Kp will increase. So if we've got more products, that tells us that the equilibrium is shifting to the right. In other words, the forward reaction is being favoured. So therefore, I need to know whether the forward reaction is exothermic or endothermic. So if the forward reaction is exothermic, then that will be favoured as temperature decreases, and therefore Kp will increase. and then vice versa. If the forward reaction is endothermic, then that would be favoured when the temperature increases. If we add a catalyst to a reaction that's at equilibrium, it will have no impact on the position of equilibrium, and the reason for that is that the forward reaction and the reverse reaction are both sped up, and they're both sped up to the same degree. Thank you very much for watching, and I hope you found that a useful contribution to your A-level chemistry revision. If you did find it useful, don't forget there are lots of other videos on the channel to help you practice the calculations, and don't forget to like and subscribe for more A-level chemistry videos coming soon.